You know, when Claudio invited, I was, of course, thrilled to come here again. And you know, when I first came as a graduate student in the mid-'60s in the University of Toronto, this university was just getting started, heard a lot about it, and visited it many times. And a unique model, and certainly has become a very leading university in Canada, in the engineering area. Pleasure to be here. What I'm also, impressed about, I didn't know you had an organization called WISE. It's such a, wise move. Later on, I'd like to know, I know you have to rush back, and with others, I'd like to know more about how it's functioning. I went to the website and looked at a few, things you're covering or intending to cover. As you'll see, a lot of what I'm going to say relates to those. Okay. Yes, let's talk about power systems in the 21st century. The industry, with its humble beginning in the 1880s, has grown into one of the largest industries in the world. Okay, in fact, the earliest power system built in the Pearl Street system in New York, was mostly for lighting and so on. Nobody thought, the electric energy would play such an important role in the society. Okay. The industry has done a very good job of meeting the energy needs of the 21st century. Industrial revolution, energy was very, very important. And in fact, electricity has become a basic necessity in modern society. Next to water and air, where else? Everywhere we turn, electricity plays a part. It's in the kitchen, going to go to factory, go to your office, sit in your workplace. Everywhere there is electricity, playing a very important role in the way of life. Well, the industry has done a good job. We as just, people in the industry have done a good job of, achieving these, significant achievements. We have had some negative impact as well, particularly in the natural environment, okay? And that's getting a lot of recognition. The other thing that's changing is, by the way, this is a mature industry and everything was settled, and there was a misconception that, it's, in terms of technology and everything, it's all, well established. It's far from that, as we'll, discuss today. And I'm sure many of you appreciate. Also, the energy is getting a lot of attention from the society and from our politicians and so on. The industry itself is going through major restructuring, okay? Shift from a monopolistic to competitive structure. Utilities used to be vertically integrated, and then basically, monopoly supplying. Now that's, changing all over the world. Also, many, new economic and social pressures. We'll discuss them. Okay? So, in order to play our role and, meet the new needs, we need to refocus our business so as to meet the energy needs of the society in a way that leads to long-term sustainability. That's, again, a very widely used word. It means different things to different people. What is sustainability? The way some of us look at it, it involves balancing economic growth, social progress, with the preservation of the natural environment. It's balancing all these, requirements. So, to meet, achieve our goals in sustainability, the business practices have to be built on 3 pillars of sustainability, as I call them: environmental sustainability, economic sustainability, and social sustainability. So our challenge as an industry, as well as consumers of energy as well, as we'll see, have a role to play in this regard. Our challenge is to produce, not only produce, but transmit and utilize energy in an environmentally responsible manner. Reduce cost by improving business practices and operating efficiency. Enhance reliability and quality of power supply. All these are, challenges that we'll discuss. Okay? Let's talk about the first pillar, environmental sustainability. Okay? What does it take? And we need to integrate green thinking into our way of life and business practices. Whenever we make decisions, take actions, behind that we have to have this green thinking, as I refer to here. What does it take? Minimize environmental impact of power plants, not only power plants, all other equipment. And some of them I'm going to highlight, okay? Also, maximize resource conservation. How we use various resources. This leads to environmental as well as economic sustainability. And more importantly, utilize electricity and energy in general in an efficient and smart manner. As a society, our needs were met well, but we were a bit, wasteful in a way we used our energy, etc. We could do a better job in that respect. Okay. Yeah. Let's talk briefly about environmental concerns related to power generation. Of course, a lot of, it's getting a lot of publicity. Greenhouse gas emissions is particularly CO2 emissions and so on, getting emissions. Global warming issues, of course. Also, local emissions, I highlighted it because that often doesn't get as much attention. This is a newspaper clipping. By the way, I gave on a panel session, I was just talking about this, and this was the IEEE, general meeting in 2003. It was in Colorado, Denver. As I was coming back, sitting in the lounge, airline, waiting for my airline, I picked up this paper, and it impressed me. This is power plant pollution that's tallied. This is reported from Austin, Texas. Air pollution from coal-fired power plants causes about 24,000 premature deaths a year nationwide. And there are other things. Again, pollution from power plants can be a significant cause of health problems such as cancer, heart attack, addition to asthma attacks, and so on. Again, this is no way to meet our energy needs. There are better ways. Okay, so there are these concerns, global as well as local emissions. How do we address this? Among other things we're doing, increasing dependence on renewable resources. We'll talk about what are they, how do we manage it, etc. Also, significant increase in use of natural gas, relatively cleaner form of fuel. More importantly, as I'll discuss, biofuels as well. Okay? Again, these are the sources of energy. How do we use them is an issue, which we'll discuss. Okay? Coal is there. We're going to continue to depend on it, particularly in some parts of the world. But how we use it matters. For years, we talked about clean clone technology. As an industry, we haven't. It's mostly talk, and not much has been done. Okay. Nuclear option. By the way, I've been giving IEEE distinguished lectures on this topic all over the world for 7-8 years. And one of the well-attended lecture I gave was in Ireland in 2003. The reason I mention is there is an organization called Sustainability Ireland, which co-sponsored it with IEEE. There were 200 people, government officials were there, and a lot of people were there. Sustainability was a big thing. The reason I'm saying all this is, I just had this one bullet, revival of the nuclear option. They got an email saying that this guy is promoting a nuclear bad stuff and so on. You see how the world has changed now? You probably know, Finland has just built a nuclear plant, the greenest of all countries now added. So in the mind of people, that has changed as well. Certainly, it's a matter of managing it properly. One of the ways we meet this, this goal, okay? Again, the key thing is the general trend would be towards a carbon-free electricity, and hope this doesn't surprise you, hydrogen energy economy. There's a good reason I'm introducing hydrogen. Again, as I said before, I was impressed. I saw that in your website as well. I'm not sure exactly what you guys are doing. I'd be happy to discuss that with some of you. Okay. Now, in terms of the technology drivers that will help meet the future energy needs, in terms of primary sources of energy, technological advancements, and cost reduction combined with novel application. Again, I underlined it to get your attention. Apart from the technology and how we apply it is all the important matters. Of renewable energy technologies, of course, these are the various renewable energies, bioenergy, solar, geothermal, ocean, wind, of course, is, whether rightly or wrongly, getting a lot of attention. And you probably have heard, Denmark started it all. By the way, I go to Denmark a lot, give courses and so on. Vestas and others invite me. They're, big in this. And Germany and Spain have had targets for generating 30% of electricity from wind. I think they've reached about 15% now. Now in Germany, they're having second thoughts about it for two reasons. Of course, the real cost of integrating is one thing. Also, wind power is fluctuating. The reserve generation you need to provide is so expensive. The overall advantage they perceive to get from this source of energy it's again one of the sources, but the attention it's been getting in recent years is probably going to slow down a bit. But I highlighted two areas in green. I'm going to talk more about it: bioenergy and ocean energy for good reasons. Okay. Also, complementing all this, particularly with these solar and so on, wind, you need to store good ways of storing energy. Okay, even nuclear for that matter. You need good ways of storing energy as well, as I'll discuss. So, advanced batteries. Some of you must have heard about it. VRB technologies, 2 megawatt, 3 megawatt units, etc. 60–70% efficient. Okay. Hydrogen, more importantly, as I'm going to discuss. Okay. So these are some of the things that we need to work on, or some development is going on. The other key area is, in terms of technology drivers, more distributed energy technologies, fuel cells, microturbines. Among other advantages are, I'm going to talk about environmental related issues. The other issues are, these are installed at points of consumption to reduce peak demand. In other words, in terms of the primary sources of energy in large power plants, you're reducing the dependence on the capacity and so on. Reduce peak demand. Also reduce transmission costs. And again, people are opposed to building transmission lines now. You probably know in Ontario, we don't want to see any. Not only Ontario, I don't know if some of you have heard, I mentioned Denmark, everywhere you go you see wind turbines, but the government doesn't like the transmission towers. Okay? No, seriously. Government is imposing the a transmission company to get rid of long 400 kV AC transmission lines, replace them with cables. Again, those of you who know the technology, what the problem is. These are 200 kilometers and all that. So there is a lot of those issues as well. Among others, if you can generate electricity where the loads are to the reasonable extent, a lot of these issues would be partially addressed. Also, improve power quality and security. In what sense I'm going to describe, they will improve security. Okay, and the other key driver is technologies for complementary use of electricity and hydrogen as energy carriers. Okay? I'll talk about hydrogen and try to explain why I'm adding hydrogen here. We're talking about electric power systems. What's the interest in hydrogen? I'm going to discuss that in detail. But before that, let me talk about ocean energy. Okay? Most of you probably know there are different forms of tapping energy from the ocean: tidal current energy, tides, currents, thermal, salinity gradient, temperature difference, and so on. Wave energy. Okay? And it got a lot of attention in the last 20 years. Many pilot projects built in many parts of the world. But one problem that they were running into is how it would affect the aquatic life. Fish and so on would be negatively affected, among other problems. By the way, we at PowerTech, and as Claudio explained, I was president of PowerTech Labs for about 16 years. At PowerTech, we were involved in a project. We built a pilot plant there in Vancouver Island, in a place called Race Rock. In the Pearson's College is there. People from all over the world come from university there. Anyway, it's a nice place. We built, using a novel turbine design. That's how we were involved. The unique feature about this turbine is friendly to aquatic life. It's been operating for about 3 years now, 4 years. You have fish are happily moving around, and the electricity is being applied to the island and so on. These are a lot of important issues, by the way. And then again, in terms of cost, here are the capital costs, 1,000, 2,000 per kilowatt, about twice that of the conventional other forms of energy. And but fuel cost, of course, would be zero. Energy cost would be 35 cents per kilowatt hour. There are companies, by the way, who are willing to come and build these plants, commercially operate it, and provided they get a contract to get the normal price, they're willing to. There's one Australian-based company now based in Seattle area. In fact, they were thinking of moving to Vancouver, with our support and so on. So they're offering to build and operate them. Okay. But the thing is, integration with the existing power system. Usually, where we have access to these sources of energy, we don't necessarily have a lot of transmission lines and so on. That may add to the cost. There are other ways of moving energy. But again, it's something we need to address. But the other key thing I want to message is, highlighted in green here, potentially a large primary energy source, of course clean and relatively cheap. If we as a society run out of all other sources of energy, there is enough energy left in the ocean. Somehow we can tap and bring out. Okay? So much energy there. Okay. Let me talk a bit about fuel cells. Okay. I'm sure all of you are somewhat familiar with it. This goes back to 170 years ago, first demonstrated in 1839 by William Grau in England. Okay. What does it do? Combines hydrogen with oxygen from air to generate electricity with water and heat as byproducts. Okay. Hydrogen may be supplied from an external source depending on the specific application. Okay. Or it can be generated inside a fuel cell by reforming hydrocarbon fuel. Any hydrocarbon fuel can be used. We'll discuss. I'll give you some details. Okay. Early days used to power tractors, and back in the late 50s, even NASA used it to some extent. Okay, but it was not didn't get a lot of use because of two reasons: relative cost and size. Okay, and those problems have been addressed now. Technology development. Okay, so recent advances have reduced cost and size dramatically. Okay, wide range of potential applications, sources of electric power in different sizes, micro fuel cells for laptops, to large units connected to power grids, 30 megawatt units if you want. Okay. Also, as I'm going to discuss, automobiles, fuel cell vehicles, and so on. Okay. Again, this is a key. I'm introducing this concept of hydrogen, as I said. I'm going to explain why. This is a key device, in the complementary use of electricity and hydrogen. Okay. Characteristics of fuel cells: PEM fuel cell, low temperature fuel cell, small sizes. Okay. For automobile application, that would be the type. Have all of you heard of Ballard fuel cell in Vancouver? And that's the kind of fuel cells there. Mr. Ballard way back was dreamer about hydrogen, and he developed that technology, and they developed PEM fuel cells. And I'm going to talk about vehicle application. All the automakers are working on it. It's the PEM fuel cells that are used for it. Okay. Phosphoric acid. More importantly, for large size, for power grid applications, molten carbonate fuel cell, high temperature, solid oxide. These are, very similar in characteristics and general characteristics. High temperature, various sizes, 3 kilowatts to 3 megawatts. Recently, molten carbonate, even at 30 megawatt unit has been applied. Among other advantages I'm going to highlight, look at the emissions. Clean way of generating electricity using hydrocarbon fuel. Nitrous oxide, solid oxide. Of course, CO2 is a different issue. Okay, you see fossil fuel power plant. What are the figures? Micro turbines. This molten carbonate fuel cell is practically zero. Very clean way of generating electricity. Okay, can you all hear me from back there? There's no mic. Okay. Yeah. With cogeneration, that is using the exhaust, heat and using it for generating, energy as well. Molten carbonate fuel cell or solid oxide fuel cell can achieve an efficiency of 60 to 70%. Can generate electricity directly from a hydrocarbon fuel by reforming the fuel inside to produce hydrogen. This, 60-70% efficiency compares with about 35%, 40% efficiency of coal plants or gas turbines. Some unique applications of fuel cells, using biofuel cell. These are, this is in California, as you can see, in the city of Tulare. Waste from dairy processing plant. Okay, what we treat as waste is used as fuel. Zero emissions, negative fuel cost. I'm sure somebody will pay you to take their waste. And again, you install this where the plants are and where the, middle of the city. Waste byproduct of beer brewing process in Sierra Nevada Brewing Company. Biogas produced from food waste, Tokyo Super Eco. In Tokyo, they have a place called Eco Tokyo Town where they're trying all these kinds of things. Again, food waste. biogas from water treatment plant in San Diego, California. So, these are examples of generating electricity, within the townships, using what we treat as waste now as fuel, zero emissions. Okay, so fuel cells are environmentally friendly alternative power generation source that can potentially yield lower cost electricity, no moving parts or anything, non-combustion, non-mechanical power generation process. Lower fuel and maintenance costs, hopefully. Okay. Now let me talk a bit about hydrogen. I don't know if that surprises you. Probably not, because as I said, in your website you indicate hydrogen. Later on, some of you can explain to me exactly what you're doing. Okay. Now, why are we talking about hydrogen here? Hydrogen is an energy carrier like electricity. Electricity is such a successful business, as I said in my first slide. It's not available in that form. It's not directly useful in that form. But still, electricity is playing such a big role. It's one of the biggest, any country, it would be one of the biggest industries. Why is that? The way we can transmit it over long distances, distribute it over wide area, when needed, more or less as needed in terms of quality, etc. It's an energy carrier. Hydrogen is similar in that respect. It's an energy carrier as well. In terms of complementary use, storing electricity has been a challenge. Batteries and not that great for storing energy. Of course, to a limited extent, they're fine. But hydrogen can be stored in gaseous form or liquid form. Keep it as long as you like and use it when you need it. So in terms of certain kind of transportation and storage, it has some advantage. So offers more flexibility for transportation and use. Also, hydrogen, by the way, it's a fuel, can be used like conventional fuel using a combustion process. But in a fuel cell, using it and generating electricity is more attractive because it's about 3 times more efficient than internal combustion engine or something like that. So fuel cell offers a more efficient way of converting hydrogen into electricity. Where do we get hydrogen? Water, H2. You see hydrogen there. Hydrocarbon fuel cells, oil, coal, natural gas, of course, biomass. Okay, so those are the sources of hydrogen. By the way, some of you might have heard of this term, hydrogen economy. Those who are caught up with this, believe in this. Significant changes in energy field tend to occur at the turns of the centuries. Early 1800s, rise of steam. Early 1900s, rise of electricity. And some of us believe early 2000, which is now the dawn of the hydrogen age. And again, I put a question mark here. By the way, interest in hydrogen energy is not new. It dates back to the early days of electricity. In fact, at Niagara Falls, when we built our power plant way back, people tell me, among others, have all of you heard of Stewart Energy? They're based in Toronto. They manufacture, electrolyzers, which generate electricity using electricity. That's the business they built. Way back, they were into all that. Early days, they were looking, is electricity going to play a role? Or is hydrogen going to play a role? And but again, there were technological challenges which have been addressed. So what are the major drivers leading to hydrogen economy now? Environmental concerns. Also, many of the problems in managing hydrogen, generating and storing, etc., they have been solved. Okay, so challenges were reduction in cost of production, that's been addressed. Safe storage at the required high pressure. In gaseous form, as I'm going to discuss, you need to store it at very high pressure. It's got very low energy density. And again, how do you get hydrogen? Primary energy source. Okay, those issues are being addressed, have been addressed to some extent. So, what does it take to form the hydrogen infrastructure? Production of hydrogen from hydrocarbons, could be from reforming natural gas, methane, or biomass. And again, carbon needs to be addressed because when you're extracting H, there is C left in it there, but you're not letting it into the atmosphere. you're collecting it where you're generating hydrogen, and you know, their decarbonization technologies have been developed, and we were involved in it at PowerTech. Also, in the western part of Canada, there's a lot of interest in this coal gasification, longer term high potential option. Again, how do you use coal is an issue, and one of the ways is to extract the H part of it. Okay. Also, production of hydrogen from water using electrolysis. It's attractive in systems with surplus electricity, limited storage capability. For example, you know, when I was working at Ontario Hydro, you know, this was, I left in late 1993. Around that time, we had, of course, you know, 60% of electricity from, you know, nuclear generation. During light load conditions, weekends, night times, etc., there is too much generation, nuclear generation sitting there, but not enough load, okay? Of course, at that time, our neighboring systems would also be light load. We couldn't sell them either. So we had to back off generation, which had some technical problems, but we are not taking advantage of that energy. Now, what we could do is, in a situation like that, using that surplus, you know, nuclear power available, use it to generate hydrogen in a distributed manner using electrolyzers, okay? Store it. Use that stored hydrogen during peak load conditions. What does it do? Of course, you're not, you know, reducing the peak capacity of the system. When you build a new plant, you know, you're saving money on it. You're also reducing, you know, when do we have maximum transmission distribution losses or high load? Now you're reducing that because you're meeting the peak load, you know, by using, you know, distributed generation. And, you know, dependence on, you know, transmission, you know, addition of transmission distribution network. So all those kinds of advantage. That's an example. So where you have limited storage capacity and we have surplus power sitting there, which needs to be tapped into. Also, development of renewable electric power resources for distributed hydro, using small hydro, solar, wind, you know, wave, etc. Okay. So again, continuing, what does it take to form the infrastructure? Development of hydrogen fueling and supply stations. Development of high pressure, you know, development of high pressure hydrogen storage and transportation technologies. As I tried to say initially, hydrogen in gaseous form has very low energy density. So to carry enough energy, you have to store it at very high pressure. So storage, safe, and, you know, and cheap way of storing it. Okay. It also, you know, again, if you're transporting it in gaseous form, you know, it has to be stored at high pressure. Okay, that's one of the issues. At PowerTech, we worked on it. I'm going to describe it. Also, hydrogen storage, high capacity and cyclable containers of storage for compressed hydrogen. Also, things like metal hydrates, etc., can be used. Okay. Now, what is the role electric utilities can play in this respect, enabling hydrogen economy? Of course, hydrogen and electricity are readily exchangeable, form, as some of us refer to, ideal energy currency pair for managing it. Okay. Hydrogen and electricity will dominate the transportation energy delivery systems in the 21st century. Will link low impact energy sources to end users. Low impact in what sense? Among others, environmental impact and so on. Okay? And to achieve this, electricity utilities are very well positioned to be key enablers of this kind of, you know, development. Industrial supply, portable power, stationary power, more importantly, transportation. To date, the role electric utilities were able to play in the transportation area has been limited. Of course, subways and, you know, streetcars, but others in terms of, you know, automobiles and so on, very limited involvement. Now, if by, you know, getting into, you know, this hydrogen area, you know, the electric utilities can be play a bigger role. Okay. By the way, as I said, at PowerTech Labs, we had a major project related to this. This is the what we call 700 project. You know, why do we call it 700 project? This is for storing hydrogen for transportation use at 700 bar at 10,000 psi. Okay. By the way, 6 automobile manufacturers, you know, were, formed a consortium with us. Toyota, Nissan, Daimler Chrysler, Peugeot, Citroën, Hyundai, and GM, of course, didn't join the consortium, but worked with us separately. Toyota was the first one to come to us. You know, they were saying we're developing this fuel cell vehicles, okay, clean, zero emissions. By the way, we're talking about emissions and health effects, CO2, etc. We talk about power generation, but emissions from vehicles is probably a bigger problem in many parts of the world. Big cities, you go to anywhere, pollution is a big problem. So this, among other things, will address it. Okay. Now, as I said, all automakers were working on it, but the challenge was, we have to use high pressure. They needed expertise, people who worked on this kind of thing. At PowerTech, with our materials group people, we had worked on it, compressed natural gas use over the years. Cylinder manufacturers also tested old cylinders and that sort of thing. We had that kind of expertise. So they came to us. So other manufacturers teamed up. Our role was, to standardize the pressure. At what pressure are we going to standardize? And after carefully looking at it, looking at size of the container, distance you covered between refills had to be at least as good as the current vehicles, if not more. So we picked the 10,000 psi. All the automakers agreed to it. Storage, onboard storage, okay, lightweight and safe storage. Okay, in the mind of people, hydrogen is somehow very unsafe thing to have and so on. The balloon, hydrogen fuel balloon bursting, etc., was in the mind of people, it's unsafe, etc. So safety is an issue, okay? So performance tests on storage tanks, regulators, solenoid valves, pressure, and those kinds of things we do. And again, cylinder storing it had to be light, and 2 cylinder manufacturers worked with us, And also safety and performance tests when, actually using on the vehicle. Hydraulic pressure cycling, filling and refilling over many times, exposure to high temperature, environmental extremes, vibration, etc. More importantly, bonfire, gunfire, etc. So, just to make sure it's safe. In fact, I don't have the slide here. I should have. We usually show some pictures or videos and so on. We have shown that if you do it right, as we have done here, it's safer than gasoline vehicles, tanks. The reason is a tank of, petrol, when it catches fire, it's a ball of fire. Hydrogen at high pressure in gaseous form, a lot of it gets diffused, okay? So it's, So as I said, we have pictures of, crushing it and so on. We put some of these in old vehicles, crash it against a concrete wall, see what would happen in case of accident, etc. We have shown that it's actually, compared to a petrol, fueled vehicle, it's safer for the reason I mentioned. But it's a matter of doing it right. And our staff were involved in developing the ISO standard for compressed hydrogen storage vehicles. A related project, okay, those are in a consortium with the automakers. This is compressed hydrogen infrastructure program. Multi-year program initiated in 2001, to demonstrate the technical feasibility of hydrogen infrastructure for transportation power generation markets as well. Funded by Canadian government and several industrial partners, BC Hydro, our parent company, Stewart Energy. I mentioned Stewart Energy. They're into hydrogen in a big way. These are the oil companies, BP, Shell, Chevron, BOC. Dynatech is a Canadian company, I think Ontario-based company, manufacturing containers, compressed natural gas and so on, now for hydrogen. JFE Container, that's a Japanese company, okay? The overall goal was to design and construct high-pressure hydrogen fueling stations, and again, supply hydrogen at 10,000 psi, first 700 bar station in the world. First fast fueling of hydrogen. We built it in our facilities and then designed and built a few around the world. Also, lightweight mobile trailers for transporting hydrogen, big trailers and big containers moving hydrogen to various fueling stations. And testing of vehicles from developed by the 6 automakers. This is the first plant, fueling station built. It was behind my office, and supplying, hydrogen at 10,000 psi. This was a Ford fuel cell vehicle, that was going through. I just have it there. Okay. Again, as I said, this is a self-service. Like you go, and our summer students were able to use it. course, it's at high pressure. It's a matter of doing it. So we have shown this can be designed and operated safely. Okay. Another somewhat related, just to see how we can manage our energy needs, how in the past we have not been paying enough attention. This is a BC Hydrogen Highways Integrated Waste Hydrogen Utilization Program, IWUP. What it is there is a chemical plant, ERCO, in northern part of Vancouver. This is an electrochemical sodium chlorate plant. And one of the things, waste from the plant is hydrogen. They were letting it to the atmosphere for years. So, this is a 3-year project that we were involved in, Zachary Davy Engineering and PowerTech Labs with 8 other organizations were asked to look into it. And basically, tapping hydrogen and storing it and building fueling stations for supplying it. By the way, from this one plant, there's enough waste hydrogen to supply 20,000 vehicles. Okay, clean, and again, it's energy that's been wasted. And, it's an example of how we could tap into various sources of energy, okay? Yeah. Again, enough about hydrogen. And, coming back to, distributed generation, as I'm going to try and impress on you, offer significant economic, environmental, and security benefits. Okay. By the way, I was a planner, and for 25 years I worked for Ontario Hydro Planning. Load growth, we forecast it, and we built a power plant. Every new plant we built was bigger than the previous one. Economy of scale. There is no such, economy of scale doesn't apply anymore with these new technologies. Okay. In fact, distributed generation becoming increasingly cost competitive. By the way, I don't know if some of you have heard of this organization, WAD, World Alliance for Decentralized Energy. By the way, if you go into website, type it, it'll give you a lot of information. And they have looked into many countries, and this one study they did for US, load forecasting and then ways of meeting the, the load increase. They compared costs of future capacity development using a rigorous model for the US. They showed that using different sources of distributed generation, the cost would be 5.8 cents per kilowatt hour as compared to 8.9 conventional. So it's even cheaper as well, okay? Again, this is many, experts are involved in this. And if some of you are interested, as I said, look at their website. They've looked at a few other countries as well. Apart from all this, lower production costs, etc., hopefully a bit cleaner. Reduction of transmission costs in many cases, as we discussed. So the point is, I'm not saying all of our generation of electricity needs would be from distributed generation. Significant part of our generation could be from distributed sources. Okay. Again, reduce greenhouse gas emissions and less. The other, in terms of security of supply, less vulnerable to natural calamities and acts of terrorists, etc. Ice storm. You remember a few years ago, Quebec was blacked out, eastern part of Ontario. The transmission towers fell. Gee, if we had distributed, by the way, a lot of my friends in Ottawa and so on said, these are very, good scientists and engineers. God lost faith in, our systems to supply. Like they were without electricity for a week and so on in Montreal. And when you don't have electricity, even your hot water tank, nothing works, okay? So, whereas if you have distributed generation, at least you'll be meeting some of the energy needs, okay? Hurricane, earthquake, sabotage. Again, 2003 blackout, maybe we're all blacked out too here. Again, distributed generation would meet some of the needs, okay? Again, the key thing is protection controls for these distributed sources of generation should be designed so that units continue to operate when isolated from power grid. The utility practice has been the few such sources of generation people install. Whenever there is a problem, the first thing they want to do is shake it off, rather than deal with it. Now, we want these to run, continue to run, etc. Okay, but those are all things. At PowerTech, we had a 2 megawatt, fuel cell, where we were working on designing and protection and controls, etc. Okay. Now, looking at other aspects of greening power, the electricity business, other than related to generation. minimizing the environmental impact of all equipment, not generation, etc. These are some of the examples of projects we were involved in at PowerTech. SF6 gas, you all know SF6, high voltage gear is used. But SF6, if it leaks, it's extremely potent greenhouse gas. Okay, and when you lose it, you lose some money as well, and more importantly, an environmental impact. Now we were involved in a project for SF6 gas assessment and reclamation, etc. PCBs, I'm sure all of you have heard of it. The problem with it, PCBs in liquids, in oil, etc. Insulating oil in transformers, for example, has been an issue. Many of us in this part as well, at PowerTech as well, we had built some plants for dealing with it. But PCBs in solids, like fluorescent light blast, etc., that was not addressed. Okay, they have some PCBs as well. There are plants here and there. For example, there is one in Alberta using incineration. Damage the environment, but you're getting rid of the PCB though. But we developed, using a sodium dispersion process, non-thermal, thermal, environmentally benign process for getting rid of PCBs like this. Okay. Again, a lot of the work we did in this area, Japanese were interested. We transferred the technology, and we get some royalty, etc. Again, I'm talking about how we are contributing negatively to environment, and examples of how we need to address. Another example of a project we had, environmentally friendly transformer oil, okay, vegetable-based oil as an alternative to mineral-based oil. You see, after you use the oil, if you want to get rid of it, getting rid of the oil is a problem without dumping it somewhere and damaging the environment. Whereas this is biodegradable, non-toxic, etc. So, we developed that as well. Okay, yeah. I can go on, but these are just examples. Okay, of how we address environment-related issues and meet the energy needs, etc. Let me quickly talk about the second pillar. Okay, social sustainability. Okay, I don't want to spend a lot of time. Here's the list. Okay, in terms of organization and what we need to do. Equity of customer access. We need to meet the energy needs of everybody. Okay, I highlighted this in red. Ethical business practices. That has become a big problem. And again, related to our area, Enron. What happened to Enron a few years ago? So we need to run our business in an ethical manner. Governance and control, occupational safety, employee development. More importantly, or equally importantly, community development, partnerships and networking, support for universities and basic research. I'm sure you're happy to hear that. You probably know, until a few years ago, as an industry, we weren't supporting university research compared to communication or electronics area. It was so hard to get money. As head of a department, when I was trying to provide some funding, gee, our president would oppose. Here we were handing out, the free bulbs, etc. But wherever giving money for, education and research was not a priority for the industry. Some manufacturers in countries like Sweden and so on, ABB and ASEA before that, had good interaction with universities and so on. Anyway, in the long run, we all benefit from these things. Okay. Let me talk about the third pillar, economic sustainability. Okay. This is a bigger issue. Again, what are the issues here? Efficiency, economy, and service quality. Obviously, getting a lot of attention, more important in the new environment. How do we achieve efficiency and economy? More effective use of individual equipment, as well as the integrated power system. Okay. Service quality, again, our loads are more sensitive now. Power quality is an issue, harmonics and voltage dips and those kinds of things, among other things. Again, blackouts, etc. All those are power quality, service quality related issues. So an increased focus will be on providing higher value service. At least that should be our goal. By the way, among technologies that would help us in this area is so-called smart grid technology. It's getting so much publicity. Our politicians are talking about it, media talking about it. And as we were discussing just before coming here, some of us thought it was a lot of hype and so on. But in a way, it's good. It's good to get this kind of attention from, politicians and society and so on. So let me describe briefly, what we formally consider to be smart grid concept, what the technologies are. Okay, probably some of you are into it or tap into this area. This is a formal description or definition of a smart grid we came up with. Smart grid is an electricity network that intelligently integrates the actions of all users connected to the power system, generators, transmission equipment, as well as consumers. Okay? And what's the objective? To efficiently deliver sustainable, economic, secure electricity supply. And keywords are, everybody that's part of the system, including consumers, are involved. And the key objective is intelligently integrating it. Okay? I'm going to talk about the objectives. Okay? How do we achieve it? Smart grid employs innovative products and services together with intelligent monitoring, control, communication, and self-healing technologies to achieve these goals, better facilitate the integration of generators and storage devices of all sizes, particularly when you talk about distributed resources, etc. That becomes an issue. Allow end users to play a part in optimizing operation of the system. Significantly reduce environmental impact of the total electricity supply system. And of course, enhanced levels of reliability and power. Those are all the, objectives here. You probably have seen pictures like this, a lot of them. It's more internet-looking like grid. A lot of communication between various, elements in the system. Okay. Now, specific goals, objectives: effectively engaging consumers and end users in optimizing overall power system performance. Okay. Enhancing efficiency of power system operation and reduction of capital cost, enhancing security, reliability, and power quality, enabling distributed energy sources, enabling electric vehicles and transportation, etc., which we have been talking from the beginning. Okay. What are these smart grid technologies that will make this happen? Communication and intelligence systems. Robust, reliable, secure, high-speed communication system. You see, advancements in communication technology in the last 2 decades, 3 decades has been so great, and this is, gives us a lot of, potential for, communicating between various elements in the system. But once you add these things, you're exposing yourselves to a security risk. They all have to work properly. Okay, again. What you need is robust, reliable, and secure system. And as part of smart grid, there's always this cybersecurity is an issue. But again, that's engineering. That's a matter of dealing with it. And the other technologies, intelligent electronic device, systems, devices, monitors, software as well. Okay, for online condition assessment and taking corrective actions. Is there much activity in the intelligence area here? I'm sure you are. Again, in Canada, we have an organization called Precarn, and I'm going to talk briefly about Precarn, where the Precarn's objective is to promote the advancement of intelligence technology, more importantly, apply it to various sectors, practical applications and so on, and a lot of potential in this area. Okay? So application domains, smart grid, I've listed 4 here: implementation of advanced metering infrastructure, load management, integration of distributed resources and formation of microgrids, effective use of equipment, condition assessment, performance enhancement, life extension, enhancement of the integrated power system. So these are the various application domains. Okay. Advanced metering, of course, I'm sure all of you have been affected by it now. You have smart metering here, right? Yeah, it's all over Ontario. What's the objective? Allow consumers to track their energy use. Not yet. Oh, not yet. Okay, in Toronto area. Yeah. Okay. Oh, I see. Anyway, track their energy use and participate in load shaping strategy, reduction in the and I'm also, this is secondary, so now somebody doesn't have to go and read the meter, send you a bill, etc. But more importantly, as a consumer, for example, real-time pricing, hour-ahead emergency pricing with home energy dashboard. You can have a dashboard in the house or anywhere. Time of use pricing, you can see what the price is. And as a consumer, you're trying to save money. And to the extent that's reasonable to you, you would shift your use of the load. And also, some of us, apart from money, as a contribution to the society, you would cooperate, provided you know when to have load, when not to have non-critical loads, etc. So that is the key thing. So that's getting a lot of attention, of course. In fact, in mind of many politicians, etc., the so-called smart grid is focused on this. Also, direct load control is promoted as well. I put a question mark. Again, depends on what we mean by it, how we implement it. If it's with the full cooperation of the consumer, it's fine. But I would hate the power company, utility, to come and shut down my load without consulting me, or if it's unacceptable. So we got to be careful. What did I say? Electricity is great. Why? You get it where you want, when you want, etc. That's a significant achievement. Now, if we start taking actions like this, you're going backwards. Okay. Anyway, a lot of publicity about plug-in hybrid vehicles, etc. Reduction of fueling costs, load shaping. Again, you use energy both ways. Using batteries as energy storage, feeding back. Again, one has to look at the full impact. Getting a lot of attention, as I said, and many utilities have looked at it. Among others, ERCOT and so on. There's probably some research going on as well. But the thing is, our feeders, are they capable of looking at it? And then people come and if they all start feeding in electricity, should be managed properly. But anyway, potential in that area. Okay. The other, as I said, I promoted distributed generation, etc. Energy storage as well. How do you make it all happen? It's one thing to install them. You have to manage them, and that's where this communication helps, and smart grid and technology helps. Okay. So with increase in distributed energy sources and ability to communicate with various distributed sources, formation of the microgrids has become a reality. Okay. So that's smart grid. I can go on talking about it. I just wanted to touch base on it. Again, there's so much talk about it, and I have a few other words to add to later on. But let me go back talk about technologies that will address the enhancement of effective use of individual equipment as examples. By the way, our infrastructure is typically very old, 35, 50 years old. Many of the equipment we have are reaching the end of their life. Okay. So the following technologies contribute to more effective use of equipment, operating efficiency and reliability, automated proactive monitoring system for maintenance and prevention of failures, intelligent system technology for equipment diagnostics, dynamic rating. Okay, in real time, monitor, if it's the thermal limit, monitor the temperature, etc. Again, other issues related to that. New technologies for assessment of remaining life. When do you get rid of your equipment and replace them? Sometimes, that is done arbitrarily. Improved methods of life extension, operating efficiency enhancement. More importantly, reliability-based asset management. That's become a very hot area. How do we maintain our equipment? Periodically doing it, as opposed to based on actually, the performance, etc. And this is an area, and all these areas we had work at PowerTech that we did. I'm going to describe some of them as examples. Online monitoring of transformers. As you know, in a power system, a lot of transformers. Step-up transformers, when you generate electricity, increase it to transmission level. Distribution level, there are more transformers, and again, sub-transmission, many transformers. If they fail, of course, catastrophic failures are costly, of course, disruptive, replacement cost, revenue loss, could have environmental impact as well. You probably know the way at least the big transformers are maintained. You conduct two types of tests. You tap the oil, insulating oil, look for its paper content. It's a chemical group that looks at it. Our PowerTech, we have a lot of work in that area. Also, frequency response tests. Go and conduct frequency response tests. Frequency response tells you the condition of the winding and etc. Okay. In fact, at PowerTech, a team goes. We go to, even we're invited to do work on U.S. utilities, etc. Particularly Chicago is one of our regular areas. Periodically go and test them, write a report, and come back. Okay. What we are proposing here is, what we have developed is online monitoring of condition assessment. Monitoring oil, detect condition of insulation, online, not, taking the unit down. Frequency response character using system perturbations, okay? Now that data is used, again, normally an engine scientist, chemistry person or a high voltage engineer would look at the test, write a report. Here, intelligent system software uses this data, analyzes it, and identifies any impending problems, also transmits it to control centers, okay, distribution control centers. So it's all done automatically, including analysis and transmitting the information to control centers, okay. Early detection of incipient faults and prevention of unscheduled outages and costly catastrophic failure. It's just an example of online monitoring. Staying with the transformer, for example, life extension. Of course, as I mentioned before, transformer, oil, paper ages with time and temperature. The aging is accelerated by moisture, acid, impurities, and contaminants. Okay? The condition of paper determines life of the transformer. Okay? So what we have developed here is continuously remove accelerants from the oil. Oil is circulated and it's purified continuously, and it retards aging. Extends the life of transformer by at least 10%. As I said, a lot of transformers, how many of them are you going to replace? And then are you going to do it arbitrarily, or are you going to wait until they fail? Either way, it's quite costly and disruptive. Now, this extends by 10%. We did this under an EPRI project, and it's been applied by many utilities. Okay. Another example of how we can extend the life and efficiency. Now, hydraulic turbines, hydro turbines, probably many of you know, among others, have cavitation type problems. Okay. Water passage surfaces become hydraulically rougher due to cavitation, erosion, sand erosion, corrosion, contributes to energy loss. Okay. Now, the penstock and spiral case suffer from corrosion. And what we have come up with is hydraulic smoothing achieved by using innovative coatings. These are the penstock that bring water to the turbine. So coatings we have developed. More importantly, the turbine itself, turbine runner components suffer from cavitation damage. And probably periodically what's done is, apart from efficiency loss because the profile has changed now, the surface is rough, so they go and file it. Shut down the unit, file it, okay? Takes time and money. But in terms of the configuration of the turbine, you lost the efficiency. So what we came up with is automated system for profiling turbine components. These are all hydraulic turbines. Computation fluid dynamic CFD model for various turbine components. By the way, this is how new turbines are designed, CFD type models. Okay. Abrasive water jet cutting system to profile various turbine components. 3D profiler to examine profile of turbine parts compared with CFD model. And more importantly, robotic system integrating water jetting, cutting, and 3D. It's all automated, okay? And expected increase in efficiency, 4 to 5%. See, so much hydro generation, particularly in a country like Canada. If we can get 5% more of energy, and also you're also reducing maintenance costs, etc., you're achieving a lot. So these are examples of things we can do. Okay. That's on individual equipment. By the way, there are others as well. We were heavily involved in looking at cable testing for consumers, etc., similar online monitoring, so on. Now, let's look at integrated power system, okay? Overall system performance. Effective use of integrated power system. What are the challenges? There are two issues here. The reliable, secure, efficient operation presents many challenges in this new business environment, so-called market environment. Okay? Many entities with diverse business interests. Okay? System expansion operation driven by economic drivers. and in many cases inadequate transmission infrastructure enhancement, etc. So in this new market environment, the traditional planning type design system is not taking place. That's one of the challenges. Also, power systems are physically very, very complex, cover large geographic areas, continental power grids. Of course, in North America, we always had this. In Europe, each country has its power system. Of course, they were selling and buying power. It was not operated as, now it's all one system, basically, okay? So continental power grids. And a country like India had all the electricity boards separate. They're not now integrated now, and then becoming more, larger systems. If you physically look at all the equipment there, millions of devices requiring what I refer to as harmonious interplay. They all have to work together, their performance and protection, including their protection controls, etc. Also, in terms of stability, some of you are familiar with this, complex modes of instability. Okay, problems. For example, if we had stability problems here, and if we were designing the system, we would model Ontario, New York in detail. Now, these are global problems. Entire interconnected system dynamic characteristics impact on it, inter-area modes and so on. So in terms of modeling, analysis, and taking corrective measures, etc., the entire interconnected systems have to be looked at. So the more complex and global. Okay. Again, power system security is a big issue. I'm sure all of you agree with me, particularly after the 2003, August 2003 blackout. For the industry, this was a major concern since the November 1965 blackout. I don't know if any of you were here at the time. I was a graduate student, and that's when I decided to get into power, stability area. It was an eye-opener for the society, not only the industry. Nobody expected the blackout like that, all of a sudden, it was in the evening around 5 o'clock or so, complete shutdown of power supply in, Toronto, New York, all these, all of Northeast. People didn't know. I mean, people have had blackouts before. People didn't know when it would be restored. People, after a day's work, were trying to wait in subway stations and trying to get home and so on. Elevators were stuck in the middle, and so all of a sudden, there was no electricity. And then again, as I said, it was an eye-opener for the society. We depend on it so much, and we can't just take it for granted. Somehow, electricity can be supplied, securely. And again, in the new environment, presents many challenges. Several wake-up calls, as I list them. Again, August 14, 2003. Here, August, a month later, a couple of weeks later, Southwest London, Northeast Kent. More importantly, in September, a month later, blackout of Italy. Entire Italian system was blacked out, about 60,000 megawatt of load loss, etc. A week later, a week before actually, South Sweden, Eastern Denmark was blacked out, okay, and a few others. These are examples of the challenges that we are having. We need to address them. How do we address them? Again, new technologies, improved design of operation, improved controls, particularly so-called emergency controls, deal with multiple outages, etc. Developing self-healing systems, as we call them. Intelligent controls, real-time system monitoring and control. These are all the things one could look at. With regard to control, I have one key message. One is, as you realize, overall control function is highly distributed. There are many, many, many units, generators, transmission equipment. They all have their individual controls, several levels of control, and system-level controls involve complex array of devices. But the key thing is, in addition to these automatic controls, human operators provide important links at various levels, part of the control function. Why human operator? Acquire and organize information, make decisions requiring a combination of deductive, inductive, and intuitive reasoning. It's the intuitive reasoning that's important, allows quick analysis of unforeseen and difficult situations, make corrective decisions. The most important skill of a good operator. Not all of them do it well. But anyway, if you look at the system, this is at the control center. You see their state estimator, security limits, etc. Human operator makes part of the decision process. If you look at the generation station, there are automatic controls. Human operators makes many of the control decisions. Similarly at the transmission, even at the consumer level, turning on and off, etc. So these are all done by human beings. Potentially, by the way, this is going to be a complex. Future power systems are more complex to operate in a less structured business environment. So role of human operator becoming increasingly complex. A lot of data to be analyzed, a lot of information coming in and need to be looked at. So current automatic controls do not have human-like intelligence. Add intelligence systems to conventional controls at various levels, learn and make decisions quickly, process improvise information. So basically, software type of thing. As I said, this is a big area. I'm sure there is research going on here as well. Pre-CARN, these are the intelligence systems that we were focusing on. Okay. Related to this, wide area monitoring and control. Now, with advances in communication technology, it's possible to monitor, system-wide area, with high resolution of quantities. Okay. These were major projects, WAMS project, and et cetera. Initially Department of Energy and EPRI and several utilities in the West were involved. Now, this wide area monitoring used all over North America and other parts of the world. But to date, the use has been limited to just monitoring. But potentially, it could be used for, developing what I refer to as ultimate self-healing system. Research into use of multi-sensor data fusion technology. Process data from different monitors, integrate and process information, identify phenomena associated with impending emergency, make intelligent control decision. This would be a fast and effective way to predict onset of emergency conditions, taking remedial actions. Okay? Again, all over the world it's going on. In fact, the most impressive wide area monitoring system I've seen is in Switzerland. I don't know if you go there, right? Yeah. And in fact, the E-Trans people took me to the control center. It's ABB Switzerland that have developed a very, very impressive wide area. But still, the use to date has been limited to monitoring, recording, and so on. But potentially, again, I underlined it here. This is a research area. By the way, that area, there's quite a bit of research has gone on years, particularly for defense type of applications, getting information from radars. If you look at information from a single radar, you get only so much information. It's coordinated information. And multi-sensor data fusion technology is something that helps. Okay. In terms of dynamic security assessment, real-time security assessment, probably Claudio and a few others are familiar. At PowerTech, we are the only ones supplying commercially real-time security analysis software. But it's simulations. But it looks at current system operating condition, how the system is evolving the next hour or so. It looks, in theory, at all possible contingencies, comes up with security level. Now, that can be done in the future using intelligence systems. By the way, we had a project on it, pre-CARN. I mentioned pre-CARN so many times. Yeah, okay. This was a project, POSIT, Power System Security Assessment using Intelligence Systems Technology. What it does is, it uses data collected, but using a lot of simulations. As the power system conditions are changing, there's software continuously applying contingencies, looking at security level. Also, one of the key things is, things like automatic learning, data mining, decision trees are used to build knowledge base of the intelligence systems. And looking at key parameters in the system, by the way, there's a technology available under intelligence systems. What are these key system parameters that you can use for doing this, which came as a surprise to us. Okay. Anyway, it tells, but the key thing is, you're not doing simulations real time. You capture, create this knowledge base. In real time, you look at the current operating conditions, depending on the key system variables, you can assess the security level. Okay. Also, provides new insight into factors and system parameters affecting stability. Okay. So, that was a project we worked on. Results surprised even our expectations. And this illustrates it, in real time as transactions are taking place. And, you do a lot of security analysis, store data, and using intelligence system. In real time, you assess the security level using this knowledge base. Okay. I'm almost at the end of my presentation, okay. And finally, as I tried to imply in the beginning, how we generate, transmit energy is one thing. How we use it is equally important. Smart use, enormous opportunities, exist here. Examples of smart use of power. These were major projects. Buildings for Sustainability. This was a David and Lucille Packard Foundation, Los Altos project. Basically, what they came up with was so-called living building, designed to use renewable, clean energy generated locally, minimal reliance on the grid, also efficient use of energy. We also had another project, again, Precarn was one of the organizations involved in funding it, better buildings through integrated intelligent systems, project commissioned by Industry Canada, coordinated by Continental Automated Buildings Association, SABA, and Precarn. Basically, what it came up with was reduced energy consumption, greenhouse gas emissions, improved safety and security of occupants, reduced life cycle. In a complex building like this, it would using the intelligent systems, it would use the intelligent energy in an efficient manner, with all these achievements. It's been applied on one or two major one commercial complex, one industrial complex. There's still, although it has been developed, yet to be widely used. Other examples, many utilities are doing it. For example, BC Hydro's Power Smart program, the utility paid consumers to replace inefficient equipment. Like they would visit, and if you're very inefficient equipment operating, and of course with your business you can't afford to replace it, BC Hydro paid to replace it. Why would they do that? It's cheaper to do this than build a new power plant, expensive power plant to meet the load growth. So many utilities do this kind of thing, by the way. Okay. Anyway, few concluding remarks. Of course, the challenge for us is to produce electricity that is greener, cheaper, reliable, and higher quality. Of course, greater dependence on distributed energy technologies and renewable energy technologies. Increased emphasis on the development of so-called smart grids. A few words about how we are doing so far. Current smart grid initiatives largely tend to focus on smart meters and load shaping. But potentially, we're likely to see more technology-rich initiatives in the long run. That's one thing. The other thing is, when you're applying this so-called smart grid technology, integrating everything, you need a unified vision, of the road to smart grid. Okay? All entities involved should have a common vision. Various utilities, transmission companies, generation companies, and others. And again, if you have distributed sources of generation, they all get involved, and government agencies get, regulators they get involved, and other related organizations. We need to have a unified vision, clear, picture of what is it that we are trying to achieve, and then work towards it. Otherwise, again, it becomes a disintegrated effort. Okay? So that's what I wanted to present.